Would you like to lose a little bit of weight without doing any exercise or dieting? Would you like to age just a bit more slowly than your friends? Well, you might be surprised to hear the laws of physics can help.
The key to unlocking these everyday questions is gravity. It sculpts the universe. It warps space and time. It's a fundamental force of nature. But gravity's strange powers, discovered by Albert Einstein, also affect our daily lives in the most unexpected ways. In this film, we'll be using cutting-edge scientific techniques to investigate how gravity changes your weight.
It's gone up.
Your height. I really have shrunk. And even your posture. And with the help of thousands of volunteers, I'll show you how gravity makes us all age at different rates.
Throughout the day, I've just been logging onto the phone, logging onto the app.
As a physicist, gravity is central to my work.
Oh, wow.
And in exploring it, I'll be challenged on how I understand this most mysterious force.
Wow. Okay, I need to go and write this one down.
And I'll have to tackle the very nature of reality itself. Gravity. It binds together all the matter in the universe, and it makes our existence here possible. But in the end, it all boils down to one simple question.
What happens if I drop an object?
Gravity's many mysteries are all contained in this single action: how an object falls. Here's the first puzzle. Why does a hammer fall faster than a feather? You might think it's because the hammer is heavier. But that's not the real reason. The answer is air resistance.
It's not the weight of the objects that matters, it's their shape. And I can demonstrate this very easily with these two umbrellas. They both have exactly the same weight. But if I open one of them, you can be pretty sure it'll drop more slowly than the other one.
In fact, all objects would fall at the same rate if you could only remove the air. The first person to realize this was the 16th century mathematician Galileo Galilei. Famously, it's said he worked it out by dropping objects off the Leaning Tower of Pisa. And he was spectacularly proven right in an experiment carried out on the moon in 1971.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time.
It worked perfectly.
How about that? It proves that Mr. Galileo was correct in his findings.
Now, Galileo was obsessed with a second question too.
When you drop an object, it's actually quite hard to tell if it falls at a constant speed or picks up speed as it drops. Even in slow motion, it's pretty hard to tell.
But Galileo realized this. First, drop an object a very short distance. It lands with very little impact. But of course, drop it from higher up. This time, the ball easily breaks the tile, which means it must have accelerated, gaining in speed and momentum as it dropped. Galileo had identified something fundamental to all falling objects. They accelerate. He realized there might be a way to measure how much falling objects gain in speed. What he devised was the first ever attempt to measure gravity itself.
he built a long wooden ramp, rather like this, that he had sloping at a shallow angle. The idea was to roll balls down the ramp and measure their acceleration. The crucial thing is that the ramp had to be at this shallow angle to reduce the effects of wind resistance. It also meant that the balls would roll down slowly enough to give him time to measure their speed. But the big problem was this: how do you measure time accurately in an age when there were no accurate timepieces, let alone stopwatches? Well, Galileo came up with an ingenious idea involving the flow of water, essentially measuring time from the amount of water collected in a cup. So we're going to try and repeat Galileo's experiment. I say we because I have a couple of willing volunteers, Gavin and Joanna. 3, 2, 1, go.
And stop.
Okay, there's one. Now, if you come down a quarter of the way down the ramp, go.
Stop.
Okay, so now half of the way down, go.
Stop.
Just in time. Okay, and then 3/4 of the way down, go.
And stop.
Right, turn the tap off. Okay, so we have our 4 measurements, and I can see a progression from fuller to emptier. But what we need to do now is find the mathematical pattern by weighing carefully the water in each glass.
Weighing the water should give us an idea of how long each roll took. And in our experiment, these were the results. Now, there's one immediate thing you can tell. The ball really sped up the longer it rolled. In fact, our results seem to show that the time it took to cover the first quarter of the ramp was about the same time it took to cover the next 3 quarters.
Right.
So we have a strong hint of a mathematical pattern. Now we'll see if we're right by placing bells along the ramp at intervals which are based on the results.
Okay. This arrangement looks a bit strange because the gap between the first 2 bells is much shorter than the gap between the 3rd and 4th bells. But that's okay, because if we've got our calculations right, the ball starts off slowly, so it covers a shorter distance, and as it picks up pace, it'll cover longer and longer distances. So we should hear the bells ringing at equal intervals in time. Go. Beautiful. So, what does this all mean? What's the mathematical formula? Well, this is something that Galileo worked out. Let's say, from the start, the ball covers a distance of 1 meter in the first second. After 2 seconds, it'll have covered 4 meters. After 3 seconds, 9 meters. After 4 seconds, 16 meters, and so on. If you recognize this progression, you'll see that distance goes like the square of time.
Galileo had found the rate at which gravity speeds up objects. And he'd found another fundamental principle. You can measure the strength of gravity by how much it causes falling objects to accelerate. Detecting gravity has become exceptionally sophisticated these days, but still uses exactly the same principle. This is Hurstmonceau Castle in Sussex, and in its grounds lies the Space Geodesy facility. Here, Vicky uses an astonishingly sensitive instrument to detect the exact strength of gravity on this one spot.
Okay, so Vicky, tell me about this incredible gravimeter that you work with.
Okay, so this is the dropping chamber in a stripped-down version. So essentially what happens is you've got a cart that gets raised to the top, and then the cart accelerates away from a mass in the middle. And so this section here lifts off, and as it drops under free fall.
So this component in the middle, as it drops, is basically just Newton's apple falling to the ground.
Yes.
So this is a stripped-down version, but that's the real thing.
This is the real thing.
How does it actually work?
In here it's a vacuum.
So there's no wind resistance
So
as
there's
it
no
falls,
wind resistance.
right?
Inside, a laser is used to measure exactly how fast the mass is accelerating.
This is the 21st century version of Galileo's ramp and the balls rolling down. So can we get it going?
Of course, if you'd just like to press the button on the laptop.
This one?
Yep.
Okay.
So it's now communicating with it.
Oh, here we go.
There we go. So it waits 5 seconds, then takes a measurement of gravity.
And again.
repeats.
Oh, and you can see the results appearing now.
Yep. Each of those green dots is a measurement of gravity with the actual number that it's getting for each one.
The unit Vicky uses has a familiar ring.
I see that the number up at the top here. So you've got this unit, microgal.
Yes, gal is essentially 1 centimetre per second squared. The gal was named after Galileo.
So we've just taken the measurement of gravity here today, and it's this highly accurate number, 981124007 microgals.
The reading means that the Earth's gravity speeds up a falling object by around 9.81 meters per second for every second it drops. Vicky tells me something intriguing. She takes a reading here every week, and she's found that the strength of gravity changes by tiny amounts over time. Heavy rainfall, for example, can cause gravity to increase slightly.
Presumably, if gravity is changing here in one spot, it'll have different values all around the world. And so you can have a gravity map of the entire planet.
That's right, yeah.
So what's the reason for these strange fluctuations? That's what I want to investigate next.
So, gravity changes as we move across the surface of the Earth. Well, this lies at the heart of a challenge that I've set 2 young volunteers. I've given them a task to try and find the place in Britain where gravity is at its weakest, so where objects would weigh the least. And I've given them just 3 days to try and find it.
The volunteers are Estrella Sendra, a PhD student.
I've been living in London for 5-6 years, and I'm originally from Seville in Spain. I'm very interested in taking part in this project because I would really like to know more about how this world works.
And Poppy Begum, a journalist who lives in London.
I did my degree in biomedical science, and I did biology and chemistry for my A-levels, but I haven't done any physics since I left school. I'm fascinated to find out more about gravity, and I actually enjoy a puzzle. I like a challenge.
Now, the team can't just weigh themselves to see changes in gravity. Body weight fluctuates naturally by a couple of kilos over the course of a day, whereas changes due to gravity as they travel around the country are going to be tiny in comparison, a matter of a few grams. So they're going to have to use sophisticated scientific methods if they want to measure gravity accurately.
And that's why the volunteers will be joined by 3 specialists in gravity science. PhD student Sonak Bose. He'll be in charge of some very sensitive measuring apparatus from the National Physical Laboratory. Sean Hughes, a geologist, who'll be using a portable gravity meter. And Andrew Ponson, a cosmologist at University College London, who'll help interpret the results. We've taken a collective weight for the team before they set off. It's 380 kilograms. So can they find the place in Britain where that'll decrease? They're setting out in Snowdonia National Park in North Wales. The railway climbs from here to the 1,000-metre summit of Snowdon. Sean takes his first gravity reading.
The inside is a mass on a beam, and you turn this counter, this dial, until you get the beam central.
By counting the number of turns of the dial, Sean can calculate the downward pull of gravity acting on the mass inside the machine. Sonak has a simpler method.
So inside the box is a 2 kilogram mass, and it's supposed to be sort of as perfectly 2 kilograms as it's possible to get. All right, and place it here.
Oh,
It's just coming under, isn't it?
1998.2 grams.
So it was 2 kilos in the laboratory, but now here it's a bit less.
It's the first puzzle. Why does a 2-kilo mass tip the scales at just under 2 kilos? And it's one which gets straight to the heart of what the challenge is really about.
Mass is often confused with a related quantity, weight. The mass of these dumbbells is fixed, it doesn't change. It's a measure of how much stuff they contain. Weight is different. It's a measure of the effect of gravity on these dumbbells, the downward force pulling them to the ground in the same way that it's keeping my feet firmly stuck to the ground. The crucial difference is this: if I was holding these dumbbells on the moon, they'd still have exactly the same mass, but they would weigh 6 times less because the moon's gravity is so much weaker than the Earth's.
So that's why Sonak's bringing along the 2-kilo mass. If it changes weight, then this should mean that gravity itself has changed. Ahead of them is the summit of the highest mountain in England and Wales, famed for its stunning scenery. Or it would be stunning if you could see it.
And this is what we came all the way up here for, this amazing view at the top of Snowdon. You wouldn't know it, but honestly, we are here.
So we're now near the summit of Snowdon, and I've set up the gravimeter again, and we're going to see what the difference in the reading is.
He has to turn the dial again and again to try and get a reading. It's clear gravity has changed, but which way? Has it got stronger or weaker? The team leaves Sean to work out his results and tries to position the scales as close as possible to the summit. But the reading is all over the place.
Oh,
It's gone up.
So it's fluctuating quite a lot due to the wind.
Oh, wow.
No.
I have to say, this is what science is always like, isn't it? It's never quite what you want it to be.
So they head inside to the cafe next to the summit.
The wind was being a bit naughty, but hopefully,
Well, I mean, now it's in
it's gonna work
0,
fine.
so it should be all right.
1998.2 down there, 1997.8.
There you go.
We've got it.
That's 0.4 of a gram off.
The mass weighs a tiny bit less. It's lost about 1/5000th of its weight. And Sean's found that gravity itself has reduced.
At the top of the mountain, we took the measurement, and we discovered that the pull of gravity had gone down. It had gone down an equivalent of 206 turns of the dial, and we worked out that that's equivalent to 219 milligauss.
So it's clear from the team's measurements, gravity weakens as you go higher and you get a bit lighter.
It's just an excuse to say, where are we, like the lightest? Who cares? But
Yeah.
in the sense that
Who does care?
it's actually really interesting. It's like an illustrative example
Yes.
of seeing how this is actually fluctuating depending on different factors.
Yeah,
And
absolutely. And that we could measure it and we could see it with our own eyes. It actually makes you think about gravity in a very active way. It's such a fundamental force phenomenon in nature, but we don't know much about it.
But why does gravity change with altitude? To understand that question, you have to get to grips with the extraordinary discoveries of the next scientific giant in our story, Isaac Newton. Born in England in the middle of the 17th century, he spent his life wrestling with so many apparently separate questions, from why things fall to the ground to why planets orbit the sun.
It took the genius of Newton to realize that there was one single equation that could answer all these questions. And here it is, his famous law of gravity. It might look complicated, but this is one of the most important equations in the whole of science. F here is the force. Now, Newton said there's an attractive force between any two objects in the universe. On this side of the equation, G we call the gravitational constant. Now, Newton knew it had to be there, but he didn't know what its value was. M1 and M2 represent the two objects, and r is the distance between them. Now, the equation tells us that the more massive the objects are, the bigger m1 and m2, the greater the attractive force. But the further apart they are, the bigger the value of r here, the weaker the gravitational force.
With Newton, what was once mysterious now became clear.
Newton's equation describes why an object falls to the ground, including his famous apple. But its true genius is that it applies to any object, anywhere in the universe. So it's a very simple and elegant way of describing some of the seemingly most complicated phenomena in the cosmos.
His law of gravitation can still be used today to explain how orbits work, to predict when a comet will return, to describe why galaxies spin, or to slingshot spacecraft around planets. Newton tells us to look for the underlying simplicity in natural phenomena. For instance, how the moon orbits the Earth.
If I let go of this apple, it'll fall straight down because of the pull of Earth's gravity. But if I throw it, to begin with, it travels in a horizontal direction, that's the direction of travel, but Earth's gravity is still pulling it downwards, so it ends up following a curved path. Now, if I throw it harder, it'll travel further before it hits the ground. And in principle, if I could throw it hard enough, I could put it into orbit. And that's exactly what's happening with the moon in orbit around the Earth. It's a combination of wanting to travel in a straight line, but also being pulled down by the Earth's gravity. So it ends up constantly falling around the Earth and constantly missing.
Newton's famous equation also explains the strange effect which the road trip team has discovered, that objects get lighter as you gain in altitude.
When I weigh myself, I'm represented by the first mass, m1. The second mass, m2, is the Earth itself. And the force pulling me down, my weight, depends on the distance between me and the center of the Earth. And that's the secret of the road trip. If you want to find the place where you weigh the least, then you have to get as far away as you can from the Earth's core.
So it's the afternoon of day one, and the road trip team have to work out where to go next. Poppy and Estrella have a good idea. Find somewhere higher than Mount Snowdon.
From the measurements that you guys did at Mount Snowdon, altitude clearly plays an important part in gravity. So with that in mind, we've got to go to the highest point in the UK, which is Ben Nevis.
OK, but there's just one thing that we haven't shown you so far. We actually brought along an extra experiment. So can we please show you this first before you make the final decision?
Yes.
Sonak actually has the other part of this experiment. We always carry around
some power tools, as physicists always do. So let's start off nice and gentle. OK, and then try and pick up some pace.
Pizza.
And
you got some pizza there.
Point proven.
The point is that when something is spinning, it kind of gets flung outwards.
Yeah.
And you can actually use that to make a nice flat piece of pizza. But this also applies to the Earth.
The Earth isn't perfectly round. It's what's known as an oblate spheroid. It bulges at the equator where the spin is greatest.
We've kind of got two competing effects now. We're trying to get away from the center, the actual core of the Earth, the point at the very center of this ball. But now we can do it in two ways. We can either kind of go up something tall, or we can just go down towards the equator.
This is what we find when we're doing gravity surveys, is that as you move south, there tends to be an effect from latitude, which is usually larger than the effect from altitude.
So the closer to the equator you go, the further you get from the Earth's core, and the lighter you get.
So, guys, the sun's setting just behind me here. This is north. From the conversations we've just had, it sounds like we've got to go that way down south. Is that right?
Yep. Yep. Okay.
Let's go.
Let's go.
The team is starting to uncover the reasons why gravity changes as you cross the surface of the Earth. Our planet is defined and shaped by the complicated forces which act upon it. And detecting tiny fluctuations in its gravity field can give us important clues. It can help us understand how our world is changing. The Space Geodesy Facility at Hurst-Monceau is one small part in an enormous global network, which uses satellites to detect the tiniest of changes in the Earth's gravity field.
Tell me what exactly your job is here.
What we're doing with this telescope is measuring very accurately the distances of satellites from here. So we're using very short laser pulses, which we direct towards the satellite. On the satellite, there are reflecting cubes, which return some of that light to us. And we measure how long it takes the light to go to the satellite and back.
And how far away is the satellite
The one
typically?
we're tracking now is one of the Galileo satellite, which is about 20,000 kilometers.
20,000 kilometers
Yes.
away?
Yes.
Okay, so we've got it aimed at the Galileo satellite, and you're going to turn the laser on now.
Yes.
Oh, wow. And that laser beam that's being fired up towards the satellite,
Yeah.
the time it'll take to get there and come back again, it's a fraction of a second, isn't it?
It is. It's about 150 thousandths of a second, 150 milliseconds. And we're sending about 1,000 of those per second.
This strange-looking object is based on satellite readings. It's a highly exaggerated representation of how Earth's gravity field varies over time. Fluctuations like these can give us important insights into climate change. Ice caps melting, sea levels rising, changes in groundwater. All of these have an effect on the local strength of gravity.
So something as important as climate change, in order to understand it and do something about it, we need to know the distribution of the gravitational field of the Earth very accurately.
Absolutely, yes. And it's a global measure that we need.
For the road trippers, it's the start of day 2. And they're heading for the south coast. They're stopping off in Herefordshire. It's a good location, as it's the same altitude as the base of Snowdon, but they've moved about 80 miles further south. So if they find gravity changes here, it must be due to latitude.
It's not a huge difference, but it's noticeable. Our counter reading at the bottom of the mountain was 4,840.
Yeah.
Our counter reading here is 4,717.
All right. So we do get to see a difference.
So we're actually at the same altitude as the base of Mount Snowdon, but because we've travelled further down south overnight, gravity's less here.
Yeah.
They push on. And by sunset, they reach Sidmouth on the south coast. Sean takes the second gravity reading of the day. And Poppy improvises a map. Well, sort of a map.
Can we write not to scale at the top there? So I drew this map. Scotland's a bit squashed. Wales is quite high up, and Cornwall is there, but you get the idea. So, Sean, we've been travelling with you. You've done quite a few gravity meter readings. Can you plot them on this not to scale, badly drawn map, please?
Sure. So if you remember, we started off in Mount Snowdon, about here, and that was the 0 measurement for our survey. And then we've come all the way down here to the south coast. The difference from the base of Snowdon is minus 212 milligauss.
Wow.
So the difference between measuring gravity at the base of the mountain and the top of the mountain is about the same as here at this latitude and down here at this latitude.
They're quite clearly at sea level, yet gravity here is roughly the same as it is at the top of Snowdon. But where next?
We are here if we want to find out where we are the lightest, why don't we travel all the way to the most southerly point in the UK, which is here?
But altitude can also help us. So why not find a place in the country that is both low in latitude, but also is high in altitude in terms of height above sea level? Because that will get us somewhere that is really far away from the core of the Earth, whilst staying within the country.
So, the answer to the puzzle lies in a combination of two factors. How much further south should they go, and how much higher? At the end of day 2, Sean's results show that the team weighs about 80 grams lighter in total than back at the base of Snowdon. The way that weight changes is just one example of Newton's famous equation in action. But Newton had left his masterpiece incomplete. He didn't know the value of G, the gravitational constant, which sets the size of the force. To harness the full power of the equation, you need to know G. And the vital clue came with an incredible experiment conducted in London at the end of the 18th century. It was an attempt to work out the mass of the Earth itself. And it was carried out by an eccentric, extravagantly rich aristocrat, Henry Cavendish.
Cavendish was a chronically shy, deeply solitary man living in total isolation in his house in Clapham. The story goes that one day he accidentally bumped into a female servant on his staircase. He was so traumatized by this event that he had a new staircase built just for him, so this horrible incident could never happen again.
Cavendish had inherited vast fortunes and was able to dedicate his life to devising pioneering experiments, including one particularly extraordinary piece of equipment.
He set up something a bit like this. It's called a torsion balance. It involves 4 lead spheres, 2 large heavy ones which are held fixed in place, and suspended by a very thin wire is a wooden rod, 6 feet long, with 2 smaller balls on either end. Now, the crux of the experiment is the relationship between the large ball and the small ball. Now, of course, there's a gravitational pull downwards on both of the balls due to the Earth's gravity. But Newton also tells us that there should be a very weak gravitational pull between the balls. And this is effectively what Cavendish was trying to measure. Any slight movement of the small ball towards the large one should cause a twist in the torsion wire. And that's what Cavendish was trying to detect. Of course, this is all much easier said than done. The experiment was incredibly sensitive. The tiniest of vibrations, the slightest breeze, changes in temperature could all influence the measurements. So Cavendish had to isolate the apparatus inside a box and the box within a shed. He even realized that his mere presence next to the apparatus could influence things, so he had to remove himself outside the shed. What he then did was sit outside the shed and through a small hole in the shed wall, look through a telescope to detect the tiniest of twists in the wire. It was an incredibly difficult process, but after many months, he finally felt confident enough that he had a reliable result.
Cavendish found that the small balls did move. A tiny 4 millimeters. He calculated his results by comparing the density of the balls with the density of water.
In the end, the result of Cavendish's experiment and subsequent calculations was that the density of the Earth was about 5.5 times that of water. Or, put another way, the mass of the Earth was 5.9 trillion kilograms. What's most remarkable is that Cavendish got this number right to within an accuracy of 1%.
With Cavendish's astonishing result, scientists were able to work out G. Then the equation could be used to determine the mass of any celestial body in orbit around another. So astronomers were able to calculate the mass of the Sun, and the planets, and the Moon, and eventually even distant galaxies. And of course, back on Earth, we never escape gravity. Over the course of the day, it actually squeezes your spine, an effect you can see for yourself if you use a measuring rod.
Okay, so it's 7:30 in the morning. I've just got up and I'm going to see how tall I am before gravity drags me down. That's 178 centimeters, or just over 5'10".
Over the course of the day, gravity compresses the fluids in your spine.
Right, it is just past 11 p.m. I've been standing up for most of the day, so let's see if gravity has had an effect on my height. That is 176 centimeters, so I really have shrunk by just over ½ an inch over the course of today.
In the longer term, gravity can affect your posture permanently. But there are exercises you can do to counteract this effect.
Part of my research has been looking at the effects of gravity on the human body. So people might not be aware, or they might not always think about the effect of gravity on our physical state, on our health, and particularly on our posture. However, because it's such a constant force, gravity has a massive impact over the course of our lifetime.
As you get older, you can develop a stoop, which is damaging to your mobility.
Doctor here's actually got very good posture, but I'd like you to just show not so good posture. So when poor posture is really rounded shoulders and then loss of the curve in the back as well. I can't just ask you to raise up your arms when you're in that posture. So, no, and then just come back down, shoulders back into normal, and then raise your arms. You can see the effect of posture on function.
Ironically, the exercises which many gym goers do actually make your posture worse. That's if you only exercise the frontal muscles, like the chest and abdominals. So it's recommended you exercise the back muscles just as much, to straighten you out and counteract the effects of gravity. Meanwhile, it's the end of day 2 for the road trip, and they've reached Sidmouth on the south coast, looking for the place in Britain where they'll weigh the least. They've worked out the answer lies in a combination of 2 factors: the right mix of going south and being higher up. And for the final leg of the journey, I'm going to meet up with them. I asked them to drive a short distance west, to one of the most remote areas in mainland Britain, Dartmoor National Park. It's only 40 miles from the southernmost tip of Britain.
Hello! Hi, Andrew! Nice to see you!
And it's very high, very hilly territory.
Jim, the team got to the south coast yesterday,
Yeah.
where we defined gravity at its weakest. But we haven't quite figured out whether it's altitude or latitude. Do we go further south, or do we go higher up?
You're right to ask, do we go as far south as possible or as high as possible? That's why I've brought you here to Dartmoor, and we've charted the most important points on this map here.
All right.
Let's have a look. So we are here, 2 bridges.
Yeah.
These 4 dots represent these hills up there behind us, which are at about 500 meters above sea level. So that's what we want to check out.
These hills are close to the south coast, and they're also the highest in the whole of the south of England. So logic suggests there must be the right combination of latitude and altitude.
Well, there's another reason why this makes perfect sense, one which we haven't looked at yet, and that is the effect of the underlying rocks on gravity. And I've got a map here that shows...
You're going to trump my map with yours, aren't you?
Here we are, down here. Now, these blue areas are the lowest areas according to the density of the rocks underneath.
The rocks around here are made of granite, which will make gravity weaker still.
So that's helping as well as the altitude and the fact that we're further south.
Yep, it's also playing a part.
Well, we have a plausible theory, but now we need to test it. If I'm right, then at the top, our gravity reading should be by far the lowest reading of the trip. Of course, there's another effect of gravity to deal with now. It's knackering when you head uphill.
Okay, so I think this is pretty much the start of the hills we've located on the map. So let's see if this is the lightest place. Sean, if you want to get the gravity meter out, and we'll take another reading here.
Yep.
Okay.
Sean sets up his equipment one more time.
What's the news?
Well, at the bottom of Mount Snowdon was our zero for this test. We found we lost a certain amount by going up to the top of Mount Snowdon. We found we lost a certain amount coming south to the south coast. Not only have we beaten that, we've smashed it.
Brilliant.
We were minus 219 milligauss lower at the top of Mount Snowdon. Here on Dartmoor, we're minus 347 milligauss lower.
Brilliant. So it is a combination of three things. We're far south, so that's the latitude. We're at altitude, we're high up, and we're surrounded by all this granite rock, which is low density anyway. I hope you all think it was worth the climb up here anyway.
Yeah, absolutely.
There you go. Boom. Science.
Now, we already know that the altitude of these hills takes us much further from the Earth's core than anywhere else further south in Britain. So gravity must be weakest here. There's extra evidence too. The British Geological Survey has compiled tens of thousands of gravity readings made in the UK, and the lowest readings ever recorded were all taken around here, on the high hills of Dartmoor. What do we do to celebrate? We weigh ourselves, of course.
VFX weight that much.
It's all them Nutella pancakes for breakfast.
74, 75.
I need to lose weight.
I can tell you that you should weigh something like 20 grams less than you did at the base of Mount Snowdon. Guys, I'm guessing something like 25 to 30 grams less. So if you want to weigh as little as possible, this is the place in Britain to come. But in any case, it's such a tiny amount that it's going to be wiped out entirely by whatever it was you had for breakfast this morning.
In episode 2, I'll investigate how Albert Einstein's theory of gravity completely changed our understanding of space and time. I'll travel to Louisiana in the USA to listen to the sound of black holes colliding.
Biggest source of energy in the universe, one of the biggest events you'd ever measure, and we just barely saw it.
And with the help of thousands of volunteers and a smartphone app, I'll explore how the science of gravity can help you age slower.